A voltaic cell, sometimes called a galvanic cell, uses a chemical reaction to produce electrical current. Oxidation-reduction reactions involve the transfer of electrons, and they're responsible for creating voltaic cells. In part 1 of this lab, we are going to compare different metal half-cell reactions with a zinc half-cell reaction. So I'm going to start by putting a 1 molar solution of zinc nitrate in the first 2 wells there so we can compare the zinc and zinc half-cell reactions. And then I'm going to fill the rest of these wells with a 1 molar solution of zinc nitrate because we're going to be comparing all of the reactions with zinc. So my first pair of wells has a 1 molar solution of zinc nitrate in each one. Then I'll add a 1 molar solution of copper 2 nitrate, a 1 molar solution of iron 3 nitrate, a 1 molar solution of magnesium nitrate, a 1 molar solution of lead 2 nitrate, and a 1 molar solution of silver nitrate to the last well so we can compare these wells. I'm going to add my electrodes. These are all going to be zinc because, like I said, we're going to be comparing every half cell to the zinc half cell. We're also going to start off by comparing the zinc to each other. Hopefully we get a 0 volt for this because there's no potential difference between the two. But I'm going to add my metals here. These are all the same metals that are in the corresponding nitrate solutions. Now, in order for a voltaic cell to work, you need a salt bridge, which we're going to use a strip of filter paper soaked in a 1 molar solution of potassium nitrate. Now, our first test is between the zinc and zinc half cells. We have 0 volts for this because there is 0 potential difference between the 2 half cells since they're identical. Now we will move on to compare the potential difference between the zinc and copper half cells. And when you're recording positive voltages, try to record the highest number that the meter gives you. Now let's see what happens if we leave the salt bridge out and try to record the potential difference. You'll see we have 0 volts here. The purpose of that salt bridge is to maintain neutrality and keep the circuit running. Now that our salt bridge is in place, we can record the potential difference between the zinc and iron electrodes. And now we will record the potential difference between the zinc and magnesium electrodes. When you're recording a negative voltage, you want to get the most negative number that voltmeter will read. This one's a little tough because magnesium tends to have some oxidation on it, and it makes the connection not quite as perfect as I would want it to be. So you really have to do your best to try to get the lowest number on this negative voltage. Next, we will compare the zinc and lead electrodes. And finally, we will compare the zinc and silver electrodes. Now, the data we got from part 1 will allow us to create a zinc standard reduction table that we can use to calculate all of the other possible combinations. So what we're going to do in part 2 is just create a wide variety of different combinations of these same metals and their solutions and compare them against the calculations that we get from our standard reduction table. Okay, so we're going to start with copper as our anode and iron as our cathode. In this trial, magnesium will be our anode and zinc will be our cathode. Here, iron will be our anode and zinc will be our cathode. Now, silver will be our anode and magnesium will be our cathode. In this trial, lead will be our anode and copper will be our cathode. And in our last trial, silver will be our anode and lead will be our cathode.